In this module, we will apply the concepts that were discussed in Module 4.1, Interactions of Radiation with Matter. At the end of this module, you should be able to describe how gamma spectrometers record signals resulting from the photoelectric effect, the Compton effect, and the pair production effect. You should be able to discuss how software parameters such as keyline, peak centroid, energy tolerance, and full width half maximum are used to determine if a peak is valid. You should be able to identify the most common features and artifacts present in gamma spectra. And you should be able to list at least 4 factors that should be considered when attempting to identify an unidentified peak. The key concepts to focus on in this module are EPA Method 901.1, gamma-emitting radionuclides in drinking water, requires that all photopeaks in the gamma spectrum be identified. A real photopeak is characterized by a Compton edge and a Compton continuum preceding it. A coincidence sum peak results from 2 gamma rays emitted by the same nucleus. Random sum peaks arise from gamma rays emitted by different nuclei. Identifying low abundance gamma rays for the highest activity radionuclides found will require going to the decay schemes on the NuDat database. There are 3 types of gamma ray detectors that are used for gamma ray analysis. The thallium-doped sodium iodide crystal is actually a scintillation detector. The gamma ray transfers energy to the crystal through excitation of a K-shell electron via the photoelectric effect. These electrons migrate to the crystal's ground state, giving off photons in the ultraviolet to visible energy range. The crystal itself does not have a potential across it. The sodium iodide crystal is optically coupled to a photomultiplier tube. The photons from the de-excitation of the sodium iodide crystal are converted to an electronic pulse in the photomultiplier tube. The resultant pulse is proportional to the energy of the initial gamma ray. Sodium iodide detectors are operated at room temperature, are very rugged, relatively cheap, and easy to operate, and they are not significantly affected by temperature or humidity. However, they have a limited ability to distinguish between gamma ray peaks that are closer together than about 80 keV. There are 2 types of germanium detectors. The older version was a lithium-drifted crystal of purified germanium. It began to be phased out in the early 1980s when the production of high-purity germanium became a more routine practice. The germanium detectors also detect gamma rays via the photoelectric effect, but these crystals are cooled to liquid nitrogen temperatures and have voltages applied to the crystals of about 2500 to 4000 volts. In the germanium detectors, the photoelectron is accelerated in the voltage field applied to the crystal, and it ultimately produces a pulse at the detector's preamplifier that is proportional to the original gamma ray energy. Older jelly detectors could not be warmed to room temperature, as the lithium would drift out of the crystal, making the detector inoperable. Today, most labs use high-purity germanium, or HPGE crystals, where they can be warmed to room temperatures and then cooled back down again and operate as well as they did when first used. However, each electronic component of the high-purity germanium system has a separate power source required in order to get the high degree of resolution required for exacting gamma ray analysis. Compared to the sodium iodide detector, the newer high-purity germanium detectors are relatively expensive, more difficult to operate, require constant liquid nitrogen conditions to operate, and are sensitive to environmental conditions of the counting room. However, the big advantage of the high-purity germanium detector is that it can resolve 2 gamma rays that are within about 0.8 keV of each other. This is a significant advantage, as many samples have naturally occurring decay products of uranium and thorium that have multiple gamma rays. Finally, a significant advantage of using a high-purity germanium is that the sample can be analyzed directly for gamma-emitting radionuclides, achieving detection limits as low as 1 picocurie per liter in aqueous samples. Later on in this tutorial, we will be able to compare two spectra, one using a sodium iodide detector and one using a high-purity germanium detector, to see the differences in these two detector materials. The chart on the right summarizes the differences in the two types of detectors. Gamma ray spectra are much more complex than that of alpha or beta particles. Part of this is due to the fact that any gamma has the ability to interact with the detector crystal in one of three ways. As discussed in Module 4.1, these are the photoelectric effect, the Compton effect, and the pair production effect. EPA Method 901.1 is used for detection of gamma-emitting radionuclides in drinking water. This method requires that all gamma ray peaks in the spectrum be identified. The material we discuss in this module will provide the theoretical background for identifying the various sources of gamma rays and methods for sleuthing unknown peaks that appear in the gamma ray spectrum. Shown on this slide is a gamma ray spectrum of a cobalt-60 standard taken using a high-purity germanium detector. There are at least 10 features of this gamma ray spectrum that you will be able to identify by the end of this module. The spectrum is a plot of total accumulated counts in a channel versus the channel number. The sample was counted for about 1,000 seconds. The energy range is about 50 to 2,700 keV. In gamma ray spectrometry, the area under the gamma ray peak is a direct measure of the activity of the radionuclide associated with that gamma ray. The picture on this slide focuses on the energy range of the gamma ray spectrum for cobalt-60 below 1400 keV. Highlighted are the two gamma ray peaks that characterize the decay of cobalt-60. As you may recall from Module 4.1, these two gamma rays at 1173 and 1332 keV are almost of exactly the same abundance factor. Each one of these is called a full energy peak, or FEP, since they correspond to an energy transition resulting from the cobalt-60 decay. Each of these FEPs is a result of a gamma ray interacting with the detector via the photoelectric effect. Some radionuclides do not emit gamma rays upon decay. Some emit only one or two, and some can emit hundreds of gamma rays. The greater the number of gamma rays that result from radioactive decay, the more complicated the spectrum becomes. One of the characteristics of the gamma ray software is to have an energy identified that is unique to a specific radionuclide. This is referred to as the key line function by some software manufacturers. The key line corresponds to a gamma ray that has the largest abundance, or has the least amount of interference from other gamma rays, or sometimes it is neither and sometimes it is both. This function does not always need to be selected. In those cases, the software will determine the identity of the peak based on possible gamma ray energies in the library that are close to the measured energy. This is another preset function. The peak centroid is the midpoint of the gamma ray peak. It is determined by the peak search algorithm used in the software. The centroid will generally not be one of the discrete channels used to store information from the detector system, as the peak shape is a smoothed function. The centroid is used as the means for determining the energy of the gamma ray peak and also the full width half maximum, FWHM. This will be discussed shortly. The value of the centroid is compared to the gamma ray library to determine which radionuclides could correspond to this gamma ray energy. The picture on this slide shows the location of the centroid for the 661.6 keV gamma ray for cesium-137. The FWHM is the difference in energy between the 2 points in the peak where we measure 1/2 the number of counts registered at the peak centroid. For a high-purity germanium detector, the value of the full-width half maximum varies directly as a function of energy. During initial calibration of the detector, the software will calculate a curve for the full-width half maximum as a function of energy and use this when analyzing samples to assess whether a peak has a good shape. The table at the right shows the expected full-width half maximum for a certain detector at various energies. This was determined during the detector's initial calibration. Once a sample count is completed, the software determines this among other parameters. It will take the energy of the peaks found, calculate a theoretical full-width half maximum, and compare this to the actual full-width half maximum. If the measured value is a pre-selected value beyond the theoretical value, the software will flag the peak as having a poor shape. There may be several reasons for this: temperature shift in the room, humidity shift in the room, spectral interference from a gamma ray that is very close in energy. When a peak that is used to quantify a radionuclide has a suspect peak shape, the analyst must examine the spectrum and try to assess the reason for this. Some hints for how to do this are shown on this slide. In most cases, you will find that there is an environmental effect in the laboratory responsible for the poor peak shape. However, if there is no conclusive evidence that this was the cause, chemical separation may need to be performed for the analysis of that radionuclide to remove or mitigate the effect of the interfering radionuclide's gamma ray. The energy tolerance is a user-selected value that tells the software how far from the library-listed value you will accept the identity of a gamma ray peak. For example, the library has the gamma ray energy for cesium-137 listed as 661.6 keV. You, the user, have selected an energy tolerance of 0.5 keV. A sample has a peak centroid measured at 660.9 keV. Based on the selected energy tolerance, the lowest energy the software thinks that cesium-137 can have is 661.1 keV. It will not identify this peak as cesium-137. This makes the process of checking your library and ensuring the correct energy listed very important function. Keep in mind that the peak centroid will shift due to minor fluctuations in temperature, humidity, line voltage, and background radiation from other radionuclides. Thus, when the user selects a delta keV preset value, it should be based somewhat on the experience with the instrument at hand and the type of samples being measured. The user is allowed to select an energy tolerance that identifies to the software the maximum amount that the measured energy of a gamma ray can be different from the library value, and still have the software decide that it belongs to a particular radionuclide. Energy tolerance values are usually in the range of 0.8 to 2.0 keV. The higher the activity of the sample, the larger the number of counts in a gamma ray peak, and thus the easier it will be for the software to determine the peak centroid and thus the gamma ray energy. For high activity samples, the energy tolerance should be on the lower end towards 0.8 keV. For environmental samples, where there are few counts in the peak, the energy tolerance should be set wider, like at 2 keV. If the measured gamma ray energy falls outside the energy tolerance of any gamma ray listed in the library, it will call the peak unidentified. The user then needs to be a sleuth and determine the true identity of the gamma ray peak. The gamma spectrometer software has a peak search algorithm that locates the peak centroid, determines the shape of the peak based on the full width half maximum, and then calculates the area under that peak. Theoretically, gamma rays are monoergic, that is, a gamma ray has only one energy. This would mean that all the counts for a single gamma ray would ideally come in one channel. However, due to electronic voltage, temperature, and humidity variations, the imperfect response of the crystal, the FEP gamma ray events are spread out over several channels. The peak area is directly proportional to the number of radioactive decays of the radionuclide whose gamma ray this is, and thus proportional to the activity. Gamma ray spectrometry is different from gas proportional counting or liquid scintillation in that the software determines where the peak ends coincide with the background. Then, it takes the average of several channels above and below the peak that are in the background, multiplies the average by the number of channels in the peak, and subtracts the background from the total area. Notice in the diagram that the background is the average of the high and low energy side backgrounds drawn through the base of the peak. The several different ways that gamma rays interact with the detector crystal and the surrounding shielding allows us to observe some very distinct features in the gamma ray spectrum. These features are listed here as Compton continuum, Compton edge, backscatter peak, single and double escape peaks, coincidence and random sum peaks, annihilation peak, X-rays, and Bremsstrahlung background radiation. These features, coupled with multiple gamma rays being possible from multiple radionuclides, can create a very complicated spectrum. The next few slides explain how to distinguish artifacts from real gamma rays. Recall from Module 4.1 that the Compton effect occurs when only a portion of the incident gamma ray energy is transferred to an electron. There is a minimum energy that this interaction can occur with for each gamma ray. This means that if the interaction occurs within the detector, the liberated electron can have a finite maximum energy based on the incident gamma ray energy. All other interactions will yield electrons that are lower in energy, and this forms what is called the Compton continuum. The Compton continuum for the lower energy of the two cobalt-60 gamma rays shown is highlighted in green. Note that although the green highlighted area is associated with the 1173 keV gamma ray, that the 1332 keV gamma ray will also have a Compton continuum that tails off to lower energies. Each true gamma ray emitted from a nucleus will have a Compton continuum associated with it. The Compton edge appears in the gamma ray spectrum as a sharp drop in the background at an energy below the full energy gamma ray peak. The formula to calculate where the edge for each gamma ray occurs is shown on this slide. The calculation for the minimum scattered gamma ray energy is identified on the next slide. The edge to the Compton peak is angled slightly towards higher energy due to the background radiation associated with the spectrum. The equation on this slide identifies how to calculate the location of the Compton edge for a gamma ray. This can be very useful when attempting to identify why another gamma ray has an unusually large full width half maximum. Although there may be no way to avoid such interference without chemical separation, the analysts will know that the results of the analysis will be biased due to the change in background due to the Compton edge. One other note about Compton edges. If a peak is due to a random sum event, it cannot have a Compton peak because the random sum peak is an artifact of the detection system. When the Compton effect occurs in a medium other than the detector crystal, some of the gammas may be deflected through an angle that is 180 degrees to the original path of the gamma ray. This turns out to be the gamma ray with the minimum energy when interaction occurs by Compton effect. Since samples are placed in proximity to the detector, there is a probability that this deflected gamma will strike the detector. If this gamma interacts with the detector via the photoelectric effect, it will cause a signal that is not related to any individual radionuclide. In the diagram to the right, we see an example of a backscatter peak highlighted in green. Note that its shape is the reverse of the Compton edge, as its minimum energy is in the range of about 200 to 250 keV. This is because many different gamma rays contribute to its appearance. The Compton effect only becomes significant above about 140 keV, so that the minimum energy of scattered gamma rays is about 90 keV. Recall that one of the mechanisms for gamma rays interacting with matter is by the pair production effect. The incident gamma ray must have energy greater than 1.022 MeV in order for this to occur, since a positron and an electron are formed, both of which have the rest mass equivalent of 511 keV of energy. Also remember that positrons have a very short life, undergoing annihilation with an electron within picoseconds of their formation. When annihilation occurs, two 511 keV photons are formed. A germanium detector has a high voltage applied to it so that when gamma rays interact via the photoelectric effect, the electrons produced will migrate in the electric field to ultimately yield a signal. When pair production occurs inside the high-purity germanium crystal, the electron formed immediately begins to migrate in the electric field, as does the positron. Thus, the energy associated with the incident gamma ray is now split between these two particles. As the electron is migrating, the positron undergoes annihilation. Keep in mind that the kinetic energy of the positron begins to radiate as very low energy photons as it approaches its annihilation with an electron. These low energy photons interact with the detector via the photoelectric effect, producing additional electrons. When the positron annihilates, it produces two 511 keV photons. If one of these gamma rays interacts with the detector to yield a photoelectron, it will likely be counted with all the other electrons that have been formed in this process as a single pulse. Since all of the initial gamma ray energy is recorded, except the 511 keV photon that escaped the detector without interacting, a peak in the gamma ray spectrum appears. This peak is exactly 511 keV less than the original gamma ray energy and is called a single escape peak. What happens if both of the annihilation 511 keV photons don't interact with the detector? Then there will be a separate peak that is exactly 1022 keV less than the full energy peak. The spectrum on the right shows the single escape and the double escape peak for the 1332 keV gamma ray of cobalt-60. Note how small they both are compared to the cobalt-60 peak. Also note that there is no detectable single or double escape peaks for the 1173 keV peak. This is because the pair production effect increases exponentially as a function of energy above 1022 keV, and it is just too rare an event for the lower energy peak to produce these artifacts. Of the two artifacts, it is more likely to see the double escape peak based on the greater probability that both 511 keV gamma rays will escape the active detector area. A coincidence sum peak occurs when a radionuclide has two energy levels that decay from one to the next state in rapid succession. For reasons beyond the scope of this tutorial, it is possible that both the gamma rays strike the detector simultaneously, making it appear to the detector as a single event and recording the energy as the sum of the two gamma rays. In the case of cobalt-60, the 2505 keV state undergoes de-excitation to the 1172 keV state, and then from there to the ground state. Additionally, a very small percentage of the time, the 2505 keV state goes directly to ground state. For cobalt-60, the 2505 keV gamma results from both a direct transition as well as a coincidence sum effect. Because it has a direct transition, the 2505 keV peak has a Compton edge. However, there are some radionuclides that do not have such a direct transition. Their coincidence sum peaks would not have a Compton edge associated with it. The coincidence sum peak results from transitions in one atom. A random sum peak occurs when two different gamma rays, likely from two different radionuclides, randomly strike the detector at the same time. Again, the detector will record the sum of the two energies as one. A random sum peak will not have a Compton edge. Neither the efficiency curve for the detector nor the software can accurately compensate for coincidence sum effects. The best way to resolve this issue is to move the sample farther away from the detector and count it for a longer period of time. The exact reasoning for this working is beyond the scope of this tutorial. The annihilation peak is due either to a radionuclide that decays by positron emission or the pair production effect occurring outside the detector and the resultant 511 keV annihilation photon interacting with the detector via the photoelectric effect. This will often be a feature of the gamma ray spectrum. When a gamma ray interacts with the lead shielding around the detector via the photoelectric effect, lead X-rays are produced. These X-rays can strike the detector, giving rise to a signal at about 72 keV. In the previous gamma ray spectrum for cobalt-60, the lead X-rays can be seen as a very small peak at the very low end of the energy range. Many radionuclides decay by negatron emission. The Bremsstrahlung radiation that results will be low in energy and will be detected by the high-purity germanium detector. However, since it varies with negatron energy and the nucleus of interaction, there is no specific peak, just a general background that increases as you go towards lower energy. Shown on this slide are two spectra of cobalt-60. The one on the left used a sodium iodide detector, and the one on the right a high-purity germanium detector. The left spectrum has the 1173 and 1332 keV peaks for cobalt separated at the baseline by one channel. The full width half maximum of these peaks is about 80 keV. For the right-hand spectrum, counted using a high-purity germanium detector, the separation between these same two peaks is 159 channels, and the full width half maximum of these peaks are about 1.5 keV. It is easy to see from the comparison of these two spectra that the sodium iodide detector would never be able to resolve other gamma rays if they were between the two cobalt-60 peaks. EPA method 901.1 requires that when a drinking water sample is analyzed for gamma-emitting radionuclides, that all gamma ray peaks identified by the software be matched to a known radionuclide. When we have naturally occurring radionuclides such as lead or bismuth, there can be many gamma rays, some of them with abundances of less than 1%. Occasionally, the software will not have these low abundance gamma rays as part of the library. Anytime the gamma ray software does not identify a gamma ray, Ensure that you can match the gamma ray to a known radionuclide and that it can be quantitated to ensure that the maximum contaminant level of that radionuclide is not exceeded. This is where the gamma ray spectrometrist becomes a sleuth. We have discussed many different types of artifacts that can occur in the gamma spectrum routinely. We also now know that the instrument is sensitive to environmental conditions and thus energy shifts can occur, causing erroneous or no identification of gamma rays. Listed here are some tools that you can use to narrow down the list of usual suspects. Sometimes a literature search for low abundance gamma ray energies is required. The NuDat database is the most complete and accepted compilation of gamma ray energies for all radionuclides. If you are still stumped, determining the half-life of the radionuclide by performing multiple counts will help nail down the identity. Some tips on how to do this are noted on this slide. Gamma spectrometry is very different from other forms of radioactivity analysis. You've been exposed to the basics of how to examine a gamma ray spectrum. It requires practice to get good at it, so you should review some gamma ray spectra and their associated printouts and verify that you can compare the software results to the spectrum and identify full energy peaks and artifactual peaks on the gamma ray spectrum. Show which gamma rays single and double escape peaks are associated with, and identify most unidentified peaks using a variety of data and resources.